Okay, so last time we derived the equation of hydrostatic equilibrium. And as a reminder, this equation told us that the gradient of pressure with respect to radius equals negative density of the medium times g, when g is big G gravitational constant m over r squared. So in hydrostatic equilibrium, you have a balance between the force of gravity and the force of pressure in opposite directions, and your element is not going to move. This time, we're going to think about how you can actually solve for using the equation of hydrostatic equilibrium. You can make an assumption about the equation of state of an object, say it's a polytrope, and then solve for its interior structure. So a polytrope is a specific equation of state that relates the pressure at some point in an object with the density at a point in an object. And the form of the polytrope equation is the pressure equals some constant k times the density to the 1 plus 1 over n. This 1 plus 1 over n is often called just a gamma constant as well. In this setup, if you're assuming that this is the equation of state that applies throughout your entire body, then your central pressure is defined in terms of your central pressure is defined in terms of your central density, just plugged into this equation of state. And the n coefficient is called the polytropic index. And then this entire 1 plus 1 over n expression is called the polytropic exponent. These equations, with different values of n plugged in, are used to describe several astrophysical scenarios. So you might use these quite often. If you've taken stars or if you take stars in the future, you'll probably use it for stars. But you can basically use it for any spherically symmetric object that follows a rough relationship of this exponential form. So stars is the biggest, most obvious example. You can also use it for planets, particularly gas giants. And then you can also use it for post-main sequence stars, such as white dwarfs and also neutron stars. The difference in all of these cases is that you're going to use a different polytropic index n for each of these. Okay, so how do you actually solve this? Because we're basically saying we're making an assumption about the equation of state using this polytrope equation. We're saying that is how the pressure and the density relate. To actually solve this and get an expression for how the pressure and density vary with r, the radius of the object, we're going to start with the equation of hydrostatic equilibrium, which you will note already relates pressure and density. So we now have the equation of hydrostatic equilibrium relating pressure and density. Then we're also making an assumption that the pressure and density follows the polytrope equation of state. So we can rewrite our dPdr in terms of big gravitational constant g m over r squared, and then rewrite this in the following form. So if we actually want to solve this, we're going to first differentiate this expression and then substitute in the polytrope equation of state that we assumed. I should also point out while I write this differentiation that in the polytrope, the constant k that relates the pressure with the density expression, this is generally fixed for a particular type of star, but it might vary from star to star. Okay, so differentiating this expression that we get from the equation of hydrostatic equilibrium gives us a relationship that relates the mass gradient to the gravitational constant. And in writing this last two terms here, we've assumed mass conservation. mass conservation, what I mean by that is that the temperature or the gradient of mass with respect to radius is just going to equal 4 pi density r squared. So we've substituted that into the previous line. And the final expression that we get out of this is going to relate the pressure gradient to 4 pi g, gravitational constant, times the density. And density and pressure are both functions of r here. Okay, so this is going to be our starting point. Now we have not yet used the polytrope equation, so we're going to define a dimensionless density. So this is just a change of variables here. And we'll call this dimensionless density theta. And we're using here the same polytropic index n that we used before. So this dimensionless density is going to tell us how the density at some radius of our star or object, but I'll probably just say star because that's usually what polytropes are used for. The density at some radius is going to be the center density. So PC here is going to be the density at the core of our star at a radius of 0, times this dimensionless density to the n, where n is our polytropic index. And we're going to define this dimensionless density such that at the center, it's going to be 1, the center of the star, and then at the radius of the star, radius r, this dimensionless density theta is going to be 0 at the surface of the star. Okay, so now we can go back to our polytrope equation that we said was going to describe the equation of state of our object. And if we assume that that holds, so assume the polytropic equation of state, and the equation of state here is just going to be the relationship between the pressure and the density. You may also have temperature dependence in the equation of state, but we're just going to fold it into a single equation, the polytrope equation, that relates the density and the pressure. So again, pressure equals this K coefficient times rho to the 1 plus 1 over n. And then again, just like we did above, we can rewrite this in terms of the density at the center of our star, the core density rho c. And then we can write this in terms of our dimensionless density theta. And this also lets us write just this part right here is back above when we defined the polytrope. Let's see. Okay, right here, where we said that the central pressure is going to be just the polytrope equation, but with the central density plugged in for the density. So we're just here substituting in that central pressure into our equation of state. So we have the pressure at R equals the center pressure times theta to the n plus 1. So the next step to solve this is to plug it into hydrostatic equilibrium. And we're going to take that differential form of hydrostatic equilibrium that we derived above, but I'm going to do some variable changes so that we're now going to be in terms of our dimensionless density theta. For dr, and that is going to equal our negative 4 pi g gravitational constant times our central density, rho c, times our dimensionless density, theta n. this derivative in terms of r of theta 1 plus n is just going to be 1 plus n times theta to the n, d theta dr, which you'll notice is useful because now we have three terms in terms of theta n. So then we can rewrite this expression in terms of n plus 1 central pressure over 4 pi g rho c squared. And then that times 1 over r squared dr of r squared d theta dr. And that's now going to equal just our dimensionless density parameter to the n. Okay, so this first term in this expression is going to have units of length squared. And for something like a star, this would be around 10 to the 7 meters or so. But you would compute it for the particular object you're looking at. Often this is called A, so we're going to call this A for now. And we need to now define some more dimensionless properties. So next, we're going to define a dimensionless length. And this length is going to be defined. Okay, I have a hard time writing this one. Okay, this length is going to be defined such that our variable r, which remember was just our distance away from the center, is going to equal this length times a, where a is the constant that we've just defined in the previous part. Yes, I will maybe just copy paste that in the future so I don't make them all look different. So in this case, we can go back to our previous expression and we can substitute in our new dimensionless length. So we're going to take our expression that previously was in terms of physical distances, and we're going to write it in terms of our dimensionless length and our dimensionless density. And let's write this out. So again, all of the places that we previously had r, we are now substituting in our new variable. And what we are left with, this is exactly analogous to the equation on the previous line. You'll notice it all looks the same, but this form of the equation is called the Lane-Emden equation. This is again something that you may have seen previously in other astronomy classes. But this equation has solutions, theta, and these solutions will completely specify the density of a polytropic body. So the idea here is if you assume that an object has a polytropic equation of state, and what I mean by that is just that it follows the pressure equals K times density to the 1 plus 1 over n, that form that we wrote above, the polytrope equation, then you can use the Lane-Emden equation to find the entire profile of the star and get its density and pressure at every radius with just specifying the coefficient k and the exponent n. And as a reminder, we've defined this theta n is our dimensionless density. And then we have defined theta. It's effectively, it's a dimensionless temperature. And technically this is only true if you have an ideal gas. But effectively it's a dimensionless temperature. Okay. We also can set up the boundary conditions that are true for these properties. So again, our boundary conditions are going to be at our density at 0, 1 at the surface, where the surface is not necessarily any singular value. So you'll have to derive where your surface is, but your surface should always have this dimensionless, should have this theta equals 0. Okay, so some other issues is you could use a polytrope equation of state to describe something that is only a polytrope partially. So for example, you could have a star where only a region of its interior follows a polytropic equation of state, and that may lead to these boundary conditions that we just wrote being singular and not physical. But even if that is the case, you can still use the polytrope equation with some appropriately chosen boundary conditions to describe the physics of the region of interest. So in that case, you just have to match your boundary conditions so that you get the correct equation of state. So for the Lane-Emden equation, analytic solutions exist for n of 1, 0, and 5. As long as n is less than or equal to 5, then your solutions are going to have finite mass. And there are some commonly used indexes for if that entire polytropic exponent, which is the entire 1 plus 1 over n, if that equals 5/3, then that would be a good model for a fully convective star. You also can use the same equation for a non-degenerate but relativistic, such as something you might have in a white dwarf. And then if that 1 plus 1 over n exponent equals 1, then that would be a good model for isothermal gas. So the purpose of this equation is essentially if you choose your exponents and you choose your coefficients, then you can get pressure and density profiles to describe the entire interior of your star or planet or something else. Once you have chosen n, you only need to solve the Lane-Emden equation once, and then you can get an entire family of models, and then if you change k and your central density, those models will apply to a variety of systems. So every object that has the same n is going to have the same density profile, and you just have to change the scaling to get it to apply to other scenarios. Besides that, these models are often used for main sequence stars and planets, but they can also be used to study white dwarfs and neutron stars, which is something that you may see in the past or may have seen in past astronomy classes.